All right, so good evenings. So we will start right now. And tonight, our topics will be about one of the applications on with the model-based system engineering, and particularly used into the nuclear power plant design, focused in the what-if analysis and risk assessments. So I think it's a very interesting case study that we did back in 2024 by our colleague Ken Kawamura and other people. So if you're interested, we can share the papers with you, but we just try to look into the overview what this is story about. So before we get started, we just give a little bit background into what this is about, right? So we're looking into the whole agenda. We were actually looking into the background of the nuclear power plant domains and what the MBSE value and the use case can actually apply into these traditional, very consultative domains. We look into how we actually using the model base and to do the risk assessments on the safety reliability with FMEA, and furthermore to leveraging the models and its relationship to do the end-to-end impact analysis at the design phase. We will demonstrate how the system work and trying to understand how the workflow could be during this MBSC. And finally, we look into the technical demonstration and discussions, right? And some takeaways. So one very important aspect on the nuclear power plant is that right, safety and reliability is number one things. So that's why the developments of the nuclear power plant is actually a very long cycle times. So because first of all, they have to have a lot of checking on the safety and regulations they need to be compliant with. And once the power plant is being developed, it is expected to have a very long lifespan, and they will also having the other problems on the agings of the infrastructure. So to prepare the different wear and tear and also to do the different maintenance is become very critical. And then looking into the maintenance and the developments, everyone that is actually involved. So you will see that to build and develop the nuclear plant is actually involve a lot of different disciplines. So it's require a lot of high level communications and interdisciplinary between the different role to collaborate together. And more importantly is the knowledge transfer on all the phases. Then, of course, one of the very critical thing is to have transparency and end-to-end understanding feasibility into the whole design, and so that we're able to actually carry out the impact analysis in a very quick way, and also to support the very complex maintenance. So those are is the things that what this nuclear plant business is so difficult, and that is why we see the MBSC have opportunity to actually leveraging the benefit on that. So when looking into that, right, there are a number of different value as just what we discussed. Definitely, we are able to leveraging the models to do more through on the safety and reliability analysis. You have the end-to-end traceability, so you have to really leveraging that to do a very deep impact analysis, right? And that relationship is also allow us to do a lot of things like the predictive analysis and also the resilient engineering. So we can go into those kind of decisions. So with models, simulations, and the information that being simulate is actually allow us to support a lot of different decision-making support as well. So by unifying everything to look into, then you will see that the unified system field will be the high-level system abstractions for the entire thing. So we are able to encapsulate the complexity using the high level of abstractions to look into the system to make sure that we're able to have everything come together. So the typical life cycle, right, in the MBSE on the nuclear plant, the basic most of the challenge is how to ensure the safety compliance from the very beginning at the conceptual design down into the actual plant detail design, until go down into the construction phases and continue maintaining that transparency and safety compliance checking during the operational phase and also including the maintenance phase. As you look into that, right, the whole life cycle from conceptual until the actual operation, it took minimums 10 to 5 years, 15 years times. And also in nuclear plant, in doing the maintenance operation is extremely complex. So we see how we are able to actually leveraging the model base to carry out all the main activity from the system engineering perspective, start from requirements, compliance, traceability to the system model, to the risk assessments, and how that can in the future, right? We're going to continue using it into the other aspect. So one of the very critical important thing is that on the risk assessments, we are suggesting to leveraging the well-known methods, for example, combining the FMEA and FTA, and based on the PSA, right, the probabilities safety assessment methods. So by doing that, we have the true transparency. We are able to combine the best of the qualitative analysis based on the experience for the engineers, and then to go through the FTA, right, the fault tree analysis by leveraging the quantitative, using the probability methods to actually do the analysis on the top events down to the basic events, and then combine the two methods to validate each other from the very beginning to the end. So by doing that, we are able to leveraging a lot of simulations to automate the process and combine the best in two worlds to ensure the safety and reliability is able to carry out from the very beginnings to the end result through the conceptual designs to the detailed design and then to the construction and continue we use them at the operational phase. So that's how we see the opportunity can be leveraging using the MBSE together with the risk assessments and the method that we see here. So we are talking about the MBSE, right? Because the MBSE that we are doing this study is based on two language come from the OMG, the object management groups. So the system design for the conceptual capture, the operations, and also the functions will based on the language called the SysML. And to perform the risk assessments, we're actually leveraging the language which in the same family as the SysML called the RAAML. So the RAAML, if you don't know, is the modeling language that decided to be used alongside with SysML is actually itself extend from the SysML. So it provides the fundamental vocabulary to allow you to actually using this modeling language alongside with SysML to perform the FMEA, FTA, STPA, and so on and so forth, right? They also support the road vehicle functional safety on those, robotic and autonomous car like the ISO 26262. So it's a language that provides all the vocabulary that is necessary to perform those kind of risk assessment methods. So these two are working well together, and this is the example that we're trying to leveraging the both into these particular use cases. So the use case we're trying to demonstrate is a very simple thing, right? As you can see that if we're trying to deploy the nuclear plant, let's say that I have 4 rooms, A, B, C, and D. So each of these room is actually to surprise the different power generations in order to produce the powers. And because on the safety and reliability perspective, all the nuclear plant is actually require us to have redundancy on all the systems in case one failure occur or maintenance occur into one part of the system generators, then the redundant system can actually take over and ensure that the operation will be still ongoing and safe. So by having that, you will look into there are a lot of what if analysis, meaning that what if some failure actually happens and the maintenance is ongoing, and if I want to shut down a certain room to perform the maintenance, and then what is the impact to the entire operations, right? So that is how you see that we are able to use this very simple illustration to see that how the impact will be actually carried out. So let's say that the room A and room B has some failure happens. So with that case, meanings that, right, either the room have problems or the actual equipments have problems, it will cause the entire equipments inside the rooms to stop operating. right? By having that, it will very easily to look into the impact. And so let's say that if we are also have the power generation under maintenance, then it's mean that if room A and room B is happens to have accidents, right? And then we are actually having the redundant power under the maintenance, it will cost us the only reliable source is the operation that happens in room C. So by having that, that is how we are able to see that, the complexity into this impact analysis through the actual happening inside the power plant is extremely complex. The reason for that is because, the generator that provide the powers is actually produced by the different equipments inside the different rooms. And the different equipment is actually deployed and own the different functions. So when the room is actually having problems, it is very difficult for us to have the true analysis on which equipment is actually impacting and what function will be impacted and what operation will actually impacting in the whole operationing on the nuclear plant. Right, so let's say that room A, we have the equipment is actually malfunctions, then definitely we are able to see that, the generations that provided by the room A will actually stop. But if it happens that room B is actually the rooms having a problem, let's say caught a fire, indirectly all the equipment inside that room is actually stop operating as well, right? So those kind of impact is how we are able to using the model base to actually through the FMEA to actually do the failure mode to analyze them. So if the case that A and B are not available at the operational conditions, then if we have the redundant system, then the room C is actually able to continue to ensure that the uninterrupt operation, the generating the power will be still operating, right? So then we are able to actually handling the failure that happens. So that is why the impact analysis become extremely important, right? So by doing that, failure mode can happen without schedule. And so that during the times that if the maintenance is carry on, and if it unfortunately the failure will also happen, so what kind of what if analysis and complexity can be actually carried out through that things to understand based on the models and the impact analysis. So therefore, to have the clean system architecture that bound to all the regulation and requirements that go deep down into how the system will be actually operate through the operations, break down into functions, allocate into the equipments, and the relation to the room is become extremely important. And if we are able to actually understand the relationship, understand the possible impact into the arrangements, before the design actually carry out, we are actually able to save a lot of effort, right? Those kind of logic, as you can see, that is very dynamic. So in this particular case, that if this analysis is done after the actual room is already designed, after the equipment is already in place, the detailed system is already done, then the problem is the rework and the things that to actually trying to mitigate this kind of problems will become very costly, right? Because change of the location, change of the hardware, change of the room is always extremely costly. So by doing that, what we are looking into is the model-based way to actually capturing the whole concept and systems and carry out the system engineering concept. So in this particular paper, we are suggest in a number of different steps. So we have the step 0, which is actually allow us to capture the concept as the reference architecture for the nuclear plants. So this concept model is actually allow us to breathe in into the domain concept with the SysML, which is generic, and then to provide the differentiate the different behavior such as operations, functions, equipments, and rooms. And through that domain understanding, we are able to capture the relationship. As today, we have the advanced AI capability, then these ontology concept become even more important, right? Because when we have the relationship built out based on the concept, once it translates into the actual model design, so the AI will also have the capability to do the reasoning to check if the model is actually conceptually correct based on the concept from the domains. So then when that reference architecture is already prepared, the next step is actually import all the regulations that we need to be compliant, the plan development permits, and also to start capturing all the important requirements that have to be part of the certification and the compliance on the safety and reliability. So when the requirements is already clarified, then we also include the system requirement, and then we will start to build the system solution architecture. So as you can see that the system solution architecture is always start from the conceptual level. So allow us to understand what is the process will look like. To carry out the process, what kind of system is required and what function each system have to perform. Once that is done, then we will actually, based on the understanding on the logical architecture, and allocate the function and the subsystem into the components, the actual equipments that realize the solutions, and then to have the solution architecture. When all the design is done, before we actually finalize the specification and pass down to the detailed design phase, normally we should actually do the high-level risk assessment. That is what the MBSE is allow us to do. So we will apply the FME and FTA, and after the risk assessment is done, we're able to identify the mitigation risk as the safety requirements. And then so we have the opportunity to actually correct and improve the system architecture on the solutions before we actually finalize it and pass it down. And through this FME and FTA, we're able to also perform the what-if analysis, and we were trying to showcase the differences between using it the traditional way with Excel and the differences using the FME methods with the MBSE, right? So we have better understanding why MBSE become more and more important, especially on the safety critical systems. So when this is done, then we demonstrate you on the traceability end-to-end, right? How things actually work together. So this is the entire workflow the paper actually cover, and we're going to go through this particular demo example and see how things work. All right, so the entire workflow is from 0, 1, 2, 3, and 4. Any questions before we start to look into the detailed demo? All good? You can type your question into the chat as well, if there's any. All right, so when that is done, then let's take a look into the demo, right? So the demo, I prepared the recorded video in case, the live demo is not working, but I will try to go through the live demo and see how it works. All right, so let me open up the tools. So the tools that we are using here is the one that come from the SE Lab. Okay, so if you go to do the search on the website by use the keyword of INCOSE SE Lab, then you're able to find this particular website provided by the INCOSE. If you are the INCOSE members, you log in, you're able to request all these tools for self-learning. And if you are participating with the working groups, also, some of them is actually able to get the free license to work on the technical product as well. And today, our sample is based on the model-based system engineering SysML tools that is provided by Dassault Systems called the Katia Magic. So you're able to log in and to download the tools and learn and actually experiment it as you wish. All right. So the first step is about the ontology, the actual concept design to capture the domain term and terminology on these nuclear plants domains. And to capture the term and terminology, what they actually mean is that we are trying to understand the terms and capture the relationship. So as you can see from these particular things, right, we're trying to understand the relationship between what we call the requirements to the system functions, to the system structure, and also to the elements that is belong to the methods in the FMEA and FTA, such as the top events, the failure mode, and then of course you have the test case, right? So during the modeling experience, when this concept is done, we are able to actually using, for example, AI to actually interpret these ontology models and to turn it into the ontology and then to perform the reasoning against the model that we built, right? So how it actually works. So for example, that we will look into what is considered as requirements, such as the law and regulations, construction permit, the company safety regulation, all this pink color is what we consider as a part of the requirements. So you will see the different type of the requirements. They are interrelated to each other, such as the law and regulations cover everything that we need to be compliant with from the certification perspective. Then the construction permit is pretty much within the umbrella of the law and regulation, and so is the company safety regulation. And so that you will see that there will be the very clear derived information, so to specify the relationship between them. So it means that if certainly that we have some regulation that is out of nowhere, the ontology reasoning is able to catch those kind of mistake. Then we look into the test case that represent the maintenance plan. It will also be a part of the artifact being models by the modeling. So then we also high level highlighting them as a part of the terms, and so that you will see that each of the company safety regulations has test case or the maintenance plans to refine them to be concrete, right? So the same thing go down, the requirement can break down into like the process functional requirements to represent how the operational work, the equipment requirements, the function that is carried out by the function with of each of the requirements, physical requirements that represent related to the actual structure, the buildings, the construction requirement that is related to the buildings, right? So then each of these terms and relationship between them is actually outlined by this concept model, and how the equipments and also the building will be correspondent to the failure mode and the fault events on the FTA is also detailed here. So this is just an example, a very simple example, a simplified example to showcase that how we use the model to capture the ontology in order to ensure that when we build the models, we are able to leveraging the ontology and the reasoner to actually do the inspection if the model is correct. So this is a very important aspect from the digital engineering and also the AI era today, because one thing that you know that if you write a documents about the system specifications, there are no way for you to verify if it is correct or not. But if you're doing the models together using the ontology and the AI, you have the opportunity to actually run through the reasoner to look into your models to ensure the consistency, to ensure the correctness, right, between the models and the concept from the specific domains. So once we have the ontology model to be captured, then the next thing what we can do is actually to create the new elements. For you who may be familiar with SysML, is that SysML is a generic language and not designed for any specific domains or industry. So normally how we use the SysML is we have to capture the industry concept and then to extend the SysML in order to be able to use effectively in a specific domains. So in this case, we introduce a number of different type of the requirements based on the ontology that we just built earlier. So you can see that we have the requirements is actually able to extend the SysML standard requirement into the law and regulations, process requirements, construction requirements, so on and so forth, right? The same thing go for the relationship like the allocations, the activity turn into process functions, equipment functions, and then the block which represent the structure in SysML and turn it into the process systems, equipments, and the actual buildings. So this is how we actually leveraging the SysML language to extend them alongside with the ontology. So a very important thing is that when you have the concept, you have the extension, you always keep and maintain the relationship between them. So in model, we are able to actually capture what concept have to correspond into what extensions on the language itself. So we are able to evolve, update the concept alongside with the framework that we will use to do the modeling. So this is the step 0 that we talked about earlier. So first to preparing the concept and terms for specific domains. Now, once this is done, the next step is actually go into the regulations. So when we're dealing with the regulations, we know that regulation is some requirement that we do not have control on, right? So we are always import, those PDF as a part of the usage. Since I do not have the whole full system on the requirement management systems, then you can see that I prepare the videos. So what we do is actually we import the regulation from the PDF and put it into the requirement management system. Where we're using here is the requirement management system provided by the Dassault systems. And so once we get into the requirement management system, the first thing is we have to baseline that, right? So that to make sure that, the things that got inside here will be followed the different revisions that produced by the authority. And once it is baseline, it will use as a read-only copy in the modeling, also prevent, the system engineer to accidentally change them. And more importantly is that we have to have the traceability from the very beginning, start from the raw and regulations down into the different type of the requirements like the company safety regulations, construction permit, and the system requirement, functional requirement along way. And from each of the requirement, then further we need to break it down into how the requirement is being satisfied by the different design, by the different models, by the different constructions, right? And how the requirement is actually being covered, right? So you're able to do the certain coverage as well. So from here, you will see that once the requirements is already in the requirement management system and baseline, then we will start to carry over into the modeling's working environments to allow us to start to doing the modeling activity. So this is how this step is going to carry. And so we already see the information is already carried over, right? So this represent the gray color on the regulations and law, and then we have the construction permits that based on the conditions on what kind of a nuclear plant, what site it is, the locations that we need to compliance with. And then you will see the construction permit is always under the umbrella of the regulations. So the traceability is actually all covered here. So the traceability on the model base can be looked from the tables, but it can also demonstrate from the dependency metrics, for example, right? So the model is there, the relationship is there. It's just a matter of how you want to present those informations, right? So there are a number of different things you're able to present in a different way, table, dependency matrix, or the relationship map. So the important thing is that the information is within the models. So the first step is done, right? The concept is built. We extend the SysML now call for the concept, like we have not just the requirements, but very clearly define the different type of the requirements. Then we carry over, manage them, baseline them, and start to do the analysis and prepare the traceability. Then once this is done, we go down into the system level. So in the system level, that is where we start to look into the system architecture. So this is the high level to what we have already done and what is already captured. So you will see that each of the plan permits just onto system requirements. They will actually be the starting points how we start to design the systems, right? So from each of the system requirements, you will see that is actually correspondence into the plan and the plan permit and the regulations. And so when this is done, you will see that the requirement as a starting points, we will start to break it down into the different type of the requirements, such as the equipment requirements and the building requirements. Okay. So now this is a starting point, right? So once we do, the first thing we need to do is actually capture how this new nuclear plant should be operate. So then we actually build a very high level of the operation concept. So this is the one that you can see from the operational concept. And each of the operational concept will further break down into the functional architecture and how the operation will be carried by which equipments and what function that is performed by that particular requirements, right? So then through this analysis, that is how we're able to go down into the detail of doing that. So now you can see that each of these operations, they will have the corresponding functions that will be performed, and those logic will be there. And the beauty of the model bay is that when we specify the function, how it interact with the operations, we can actually run through the simulations and through the simulation to understand if the logic is correct, and we are able to have the different opportunity to do different analysis, like calculate the thermal through the different operation and how long the function being operated. So those kind of aspect become possible. Okay, so then of course, when all the power is being through the generator, so the generator is actually go into the AC power redundant systems. That is the main system that we're going to analyze today. Then you see the how the AC power redundant system will be actually operate by further go down into the equipment functions and look into how the equipment function will be break down through the different protocol like the safety bus and how they actually interact with each other. So you will see that the standby AC powers, we actually have source A1, source 2, and source 3 to actually ensure the redundancy based on the regulation that we have. So once the operation is done, we are pretty much break it down into the equipment functions and call for the equipment function into the redundancy in order to satisfying. You see the satisfying here to all the requirement that is actually derived down from the system, down from the regulation. So this is how we actually do the compliance, ensure the compliance checking. So now the process will then allocate into the actual plan. So we will have the reference plan to be also implemented as well. Then of course the reference plan is architected in a certain way that to support the process that we see earlier. So within the process, every lanes is represent to one systems that we responsible to perform the operations from the logical aspect. So the full nuclear process system structure will be something similar to the one that you see. So you got the nuclear plants, the stations, then you will look into what the stations should consist of, what kind of systems, what is the system characteristic, like the system consists of what kind of part, in this term is the equipment. So they all have a nice breakdown. Then we are able to actually also analyze into like the low pressure cooling injections, how many type of those cooling injection is available as a systems, right? So those are the things that we're able to analyze. So once this is done, then we are able to actually go down into the detailed design. So this is where we get into the equipments. If we have enough information, we are able to actually look into each of the system from the logical aspect and identify the implementations into the equipments. And finally, each of the equipments will also be allocated into the actual rooms that we design, right? So we know that how the room will be carry out which part of the equipment and provide what function that the equipment function will be provided from the operational aspect. Then you see all this relationship from the allocation, from the satisfying, from layer to layer is all captured by the model. So this is what the functional, what the MBSE allow us to do, and to have the very true and deep end-to-end relationship between all these aspects, all these informations. Right, so the architecture instance, normally what we need to do is to formalize everything, summarize all the finding and the decision into the system specification and pass it down into the detailed design. But because this is a highly safety sensitive systems, therefore normally we have to do is to perform the risk assessments. So one very important aspect on the performing the risk assessment is that each of the risk assessment and problems will be identified. And once the problem being identified, we need to do is to actually introduce the mitigation actions, right? So they always turn into as a mitigation requirements or safety requirement that I need to be satisfied. Then once that is done, I have to come back to the step 2 to update the system architecture to make sure that now the design is actually already include the risk assessment aspect and all the foreseen problem is already covered. right? So this cycle is actually cause a lot of delay and redundant work to be done and rework to be done. So if we can do it earlier in the development phase, we are able to save more times and resource, right? Because change at this diagram level is further pretty easy to adjust. But when the change happen in your 3D design, for example, in your schematic design, for example, the update, the changes is actually cost a lot of effort of the engineer. So now look into this risk assessment, what we're going to do. So this risk assessment is actually taking the system solution into the considerations. Then we actually start to looking into the risk assessment context, right? So in the risk assessment context, actually based on the system context that we built, you didn't see earlier, but we have the analysis on how the system should be operate, right? Like the natural disasters will actually impact how the nuclear plant will work. We need to be close to the water, so we're able to have the cooling to on times. And when the nuclear plant is operate normally, you have to actually provide the electricity, right, to all the city or the area that is intended to consume the electricity. And of course, the entire operation life cycle, you have to keep continue to the maintenance, right? So those are where the operation that you see earlier can be discovered, right? So each of them is actually able to look into the detail. So one, this system, as mentioned, that you can see the detailed traceability from the elements, right? And you can see most of the traceability relationship here is not manually created, but rather when you build the use case activity diagram, it's automatically created based on the relationship among the elements, right? So they have the end-to-end traceability can be presented not just on table form or dependency matrix, but also show as the relationship map at the one that you see. Then now we get down into the analysis of how this function will be allocated into the different process systems and equipments, and then to see how things goes, right? So that is where the data that we model earlier as the input for the risk assessments. So once we have these models take into the consideration, the next step is actually doing the FMEA. So the FMEA, we will start to considering about the level where you want to do. You can perform the FMEA at the process level, at the function level, at the equipment level, right? But FMEA normally you go through is actually through the table, the one that very similar to Excel, right? So you're trying to define the failure mode, classifying what this failure mode is come from, mechanical, electrical, software, the items that the failure mode is actually targeting or applied to. So in this case, is the equipments. It could be process, it could be operations, right? And then what is the name of the failure mode and what is the failure mode will cause, right? The local effect and the final effect and how severe it will be if it actually happens and what is the cost that can cause this failure mode to happen. What is the occurrence? Is it easy to be detected by the system itself, right? Based on this criteria, the severity, occurrence, and detectability, that is where the FMEA help us to calculate the RPN, right? Definitely, if the RPN is high, it turns to red, then that is where we need to introduce the mitigate requirement to resolve it, right? So this is the basic how the FMEA use. So a lot of people always ask, right? If something like this, I can just do as what we did with Excel. But what different than Excel here is that, you have a functional architecture. They may actually have a different hierarchy. Then the function allocate into the structure, let's say the equipments, and then you identify the failure mode, the failure items. So what happened is that, if you do not have the failure mode, if you do in Excel, let's say that I have these stations breakout as a failure mode. Let's say if this failure mode is correspondent only to the AC power. As you can see that now the model is all in the brown color. So if I say that this failure mode is target to the AC power, then you will see that because of the models and the relationship behind it, I will understand and able to showcase to me that this failure mode targeting to the AC power and the impact to the others. right? So the same go through into the functions. For example, if you can see that if the failure mode that I identify is to the structure on the actual systems, then the model based on the system and the relationship between the system and the function, it will automatically allow us to understand that if this system fail, this function will fail. And if we are able, based on the allocation relationship and identifying that what function will be also fail, it will also allow us to understand the exchange, what other things that impact will be fail. So the chain of the relationship on the models between the functions, the structure, the systems, the requirements, and the law and regulation are all in a chain, right? So when one thing that is being identified, the impact will be easily found. So this is one of the very important aspect from the traceability. All right. So once this is done, of course, you see that we introduce two mitigate requirements, and then they will be introduced. And then, of course, each of the mitigate requirement will come with a test case to actually evaluate if the problems has been resolved. So the test case will be verifying the specific um, mitigate requirements, and then we test against the system design. So it allow us to actually do the very high level of the functional from the validations on the model itself. So then, of course, we can continue to do the FTA to start to analyze using the qualitative, because the FMEA is a qualitative methods, right? So it is really depends, rely on the engineer experience, right? Where the failure may happen to what component of functions, and how is the detectability. But FTA is actually complement into the FMEA by give us the probability and the quantitative methods. So we start from the failure on the top events and start to break it down into the basic events and to identify from the basic event to the actual components, right? So then we are able to use it and then to correspondent complements into the failure mode, and then to use the simulation to calculate the probability and use it to actually compare with the the occurrence with the FMEA tool. So both of them will actually complement to each other, and using the models, we have a lot of opportunity to actually automate them, right, to make it more effective. So before we look into the what if analysis, right, since we are talking about the architecture, you will know that the system architecture is not just the structure that as you see that's simple, right? Because each of the structure behind the structure, the functions is actually produce certain things, right? So the thing that being produced is actually to capture as a part of the interface control informations that is based on the what we call the exchange. So the models will also capture about the exchange from each of the systems and the functions internally, right? So by doing that, you can see if, like for example, I have an exchange on energy, thermal will happening, then I can do the thermal analysis. And now if I do the failure mode on the FMEA into that particular system, so it will actually capture the function behind it and the exchange behind the function as well. Through that, the traceability based on the impact is not just considering about the hierarchy of the structure, the function that being allocated to it, but also including the interfaces, how these different components being interact to each other and what information being exchanged to each other. So this gives us a very, very true and deep impact analysis to look into the whole architecture. So you will see that this is actually covered. So now let's come back into the what if analysis. So in the what if analysis, definitely one thing that we want to look into is how the what if analysis work. So we will look into now the different systems being realized by the different equipments, and the different equipments will be allocated into different rooms, right? So we'll look into from this aspect, then you can see that the different equipments is being allocated to the different rooms, right? Let's say that the alternative redundant AC power source is allocated into 3 rooms, and the safety bus is allocated into the 2 different rooms, right? So with these allocations, we know that how the equipment will be placed into the different area. And then now we're able to actually looking into the matrix for the maintenance, right? Let's say that I have the rooms enabled first, meaning that all are operational correctly, right? So then everything is actually operating as expected. All the redundant system is working. Okay. Now, then let's open on this architecture. And then let me open another one. Okay, so let me open side by side. All right, so now you can see that I have the whole architecture. So what the model actually help us, right? Let's say that if the rooms 2 and 2 is under maintenance, so the room will be disabled. The moment the room disabled, it will, based on the architecture relationship, identifying that the safety bus will also be impacted, right? So you see there being highlighted. If the rooms, let's say 1.2 also disabled for maintenance, then of course, it will also indicating that the room is being maintenance and then what of the equipment will be actually impacted. So this is how the relationship is allow us to prepare a dashboard like this to support the different what if analysis. Well, of course, right, it is very obvious, right? If you have a diagrams, you know what room being disabled and what equipment will be actually impacted. But what if you're looking into in the actual operations, right? If a room being disabled, what is the impact to the actual nuclear plant operations, right? So then we are considering on the operations, we have to considering about the function being performed in each of the operation behind it. So once you're looking into from this perspective, by just understanding the room being disabled is not enough, and it become not that trivial to understand how things work, right? So in this case, let's say that every room is working correctly, all the system is working correctly, and then I can run the simulations and have it to go through the operation that we see earlier. So you will see that how the operation will be performed, and then how the information will be exchanged. And when it go to the redundant AC power stations, then you will see that how the AC power is actually working parallelly, and to ensure that, the power generations will not be interrupted. And so that now with that aspect, you see everything is working correctly, right? Without any problems. Done. So we continue on the operations. Let's stop it. So let's say that I want to actually turn off one rooms, let's say the room number ones under maintenance, and then it happens that room number 2 is actually have some accident, maybe fire accidents. Then room 2.2 is also under maintenance. If this 3 room is actually disabled, will it still working? Since I have 1.2 and 2.1 still operating, right? So now I'm able to run the simulations. So the simulation will base on the same operations that the nuclear plant is intended to be operate, walk through each of the functions that is required, right? And then to understand where the impacts is actually carried out through these simulations. Now, from here, you will see that it's actually stopped the simulation and it failed, right? So we will see the result later on. Let me enable 1 and let's just have only 2, and I will run the simulation again. So that result will be actually recorded because the entire operation is failed. So that's why the simulation is actually terminated. But in the case that I only disable 2 rooms with whatever reason behind it, then you will see that the operation is actually still carry on. The power will not be interrupted, right? So you will see that it will still continue working, but identify and show us that which function at which equipment is actually not performs correctly. So this is what the models give us the opportunity to do the what if analysis at the early phase. And so now if I stop, let me go to this models, then you will see that every single executions is actually recorded and reporting to back to us that which process is failed, if the process is failed, or actually which function is actually failed, maybe at the equipments, and the timestamp will be recorded. So now we're able to have the specifications with the full traceability, support the deep impact analysis, plus the result from the risk assessments, and promote them into the executable models to safeguard the detailed design. So it doesn't matter how the detailed design turned into, because my specification is in the model form. So I can use the models and turn it into, let's say, the FMU to test against the physical design. So you will see that the whole design will break down into the different disciplines from mechanical, electrical, software, and everything. And now we're able to actually look into how the different disciplines collaborate together, come up with the solution design, and plus some part maybe actually we buy the existing components and how the existing component and the thing that we need to develop ourselves will impact the entire operations. So we look into this as a part of the model-based system engineering that can enabling us. And we look into this kind of use case will be really very beneficial, especially we look talking about today in the nuclear cell rather than the plant, and but use it at the residential area in the Singapore region, for example, right? So this is actually allow us to do a lot of things, right? To do the high level operational safety, can continue use it to do the maintenance plan, what if analysis, trace study, and more importantly, to do the different configurations, right? We can use it to calculate the power consumptions compared to how many nuclear cell do we actually need. Those kind of analysis, right? Redundant. So this is the things that we are able to accomplish, and this is actually the paper that we introduced in this particular years. And I think that with all the nuclear-based systems that is being talked about recently, and it become one of the very, in my opinion, quite interesting things that we can the people may be very interested in, right? So again, this is the topics that we have today. So it's time for you guys to actually ask questions. Anything that you have, any question you have? Anyone? Okay, no questions, is it? Right? If no questions, we will call it a day, because I have some other things I need to take care on the AOSEC. So I will wish you a very good night. And if no questions, then we will end for today's discussions. So I hope you like it. And we will upload these demonstrations to our YouTube channel, right? This probably next week. And then looking forward to see you at our AOSEC, and hopefully you're able to join us next month on October 27 to 29. Thank you.